Well, good morning, dear, and welcome back. So, the new semester has begun, and the campus is full of students, and this is in full physical mode. And so, it is time to concentrate on our studies. So, I was discussing the linear regression model, how to develop the model, in fact, in a non iterative way. And in that context, we have deduced the normal form of equations and in my earlier lecture. And since it was done using only two features, one of them is fictitious features, which value is always one, um, that was made to make you understand the underneath principles and how to actually do it by hand. But in actual practice, the number of features could be really large. Say, for example, in housing price data, the price of the house can depend on various features. For example, floor area, number of room, number of restroom, number of garage, number of floors, then locality, where it is situated, what are the socio-income group staying over there, and all kind of, you can imagine, those are called features based on which the price of the house depends. And when these features are large in number, then we need to take the help of vector form of representation. So we need to make the predictor design in vector form. We need to reduce the objective function in vector form. Then we need to differentiate that objective function with respect to vectors. So all these things we are going to study today because this is more practical. So I told why it is needed and then how to write. So this is, say, my predictor, and this is fictitious features whose value equal to 1, and this term is called bias, as you know. And we told why bias is required in my earlier class. And then these are the real features. Say I have n number of features, and with each feature I have a parameter associated. So this is my predictor design. Now suppose I have m number of samples. Samples could be 5,000, 10,000, 500. So these are m equals to those samples. Okay. So for sample number 1, I can write the predictor expression like this. Sample number 2, I can rewrite like this. Likewise, for sample number m, I can write the predictor like this. Okay. So this notation here, whatever is in the at this place, is actually the number of the sample. Okay. And this is the objective function. And we told very interesting story that why it is squared. Okay. And 1 by 2m, don't worry about this term, because this is for mathematical convenience. We have kept 1 upon 2 times m, so that when I will differentiate this function, the 2 will be here, and this 2 and this 2 will cancel out, and I have m number of sample. So kind of average error we are trying to compute. So that's why we are beforehand dividing it by m. So this is not coming from anywhere. This is for mathematical convenience. And I will show you that in vector form, when we'll actually differentiate this function, I can just ignore it for some time, because in any way, when you will make it to 0, it will not be there. And just see. Now, this is my expression number 1, and I would like to represent it in vector form. See, so this is h is the predictor, parameterized by w, function of feature. And what is the dimension of this vector? So there are m number of samples, obviously m cross 1. Okay, this is equals to, and suppose x bar, I am calling this matrix, okay, times w. So w is actually, let us see all the dimensions right now. Okay, say W is, you see, W0, W1, W2 up to Wn. This is a vector whose dimension is n plus 1 cross 1 because it is starting from W0. There are n number of features. So that's why n plus 1. And so its dimension is n plus 1. And then what is the dimension of feature vector x? Obviously, it's like same like x0, x1, x2 up to xn. So dimension of the vector will be n plus 1 cross 1. I write it that it belongs to the range space 1 plus n plus 1. Here, x bar is defined as the designed matrix whose dimension will be, you can see, what will be the dimension? M cross n plus 1, isn't it? M cross n plus 1 is the dimension. Then only if you multiply this with this, so this gets also dimension will be m cross 1. Okay. So from here you can deduce. So it has to be, resultant has to be m cross 1. And so this is your n plus 1 cross 1. So dimension of this has to be m times n plus 1. Okay. Let us see. So far so good. Okay. And this is y is the level. Okay. Just like price for this floor area, this is the price. For that floor area, that is the price. So this is level data. Okay. And the predicted value is this. This is actual value. Okay. So dimension will be as usual m cross 1, and it belongs to, because m samples are there, so it belongs to range space m. So now what is the structure of the design matrix S bar? This is our interest. So I am rewriting this from my earlier expression. So you see, this is the predictor. Predictor for each sample I have written like this. Okay, and there are m number of samples. So x bar would be, see, x0 for sample number 1, x1 sample number 1, x2 sample number 1 up to xn. Similarly, x0 for sample number 2, x1 sample number 2. This is for sample number 2. So each row of this matrix is the feature values, all the feature values corresponding to a particular sample. Okay. So this is the matrix. Okay. And its dimension is m cross n plus 1. M cross n plus 1. Because then when you multiply it by w, you will get m cross 1. Okay. See, m cross n plus 1 times w is the parameter. Okay. So which is n plus 1 into 1. Okay. So this is vector. So by this time, all of you know the difference between matrix and vector. So vectors are actually column matrix. So it has only one column. So far so good. And that is our objective function jw equals to 1 by 2m summation of I equals to 1 to m. This is h parameters by w xi minus yi whole square. Okay. So this now I would like to represent or rewrite, in fact, in the vector form. See carefully. So jw in vector form will be equals to, sorry, that's a mistake. Okay. So this is my predicted value. This is my actual value. So this is a mistake. Please correct it. I have corrected it. So you see now h parameters by w xi I am writing. So this I can write like this. This is very interesting. Minus yi, okay, times hw xi minus yi. Okay, so this square I have written like this. And from 1 you are getting that what is HWX. HWX from 1 we have already reduced it. This is nothing but, so this is nothing but HWX. So this side which has a dimension of M cross 1, which is equal to this design matrix, which has a dimension of M cross n plus 1 times W. Okay, n plus 1 cross 1. Okay, so from here this can be written in this form, right? So I have written it like this. So JW is now equals to 1 by 2m. Just don't pay attention to this. This is equals to, in the linear algebra, you know, this square can be written into this times this. So I can write in matrix form transpose of this times this. Then it will be a square. Okay. So everybody with me? Just take a notebook and then do it with me. It's very simple. In vector form, we have written like this. Okay. And now this can be written x bar w transpose minus y transpose. Okay. So this is plus or minus is there. So minus is there. Times x bar w minus y. And we are ignoring this for the time being. That is equals to, so this multiplied by this term. So x bar w transpose into x bar w minus this multiplied by this. So this multiplied by this. So that is x bar w transpose into y. Then minus y transpose x bar w plus y transpose y. So that's it. That is the vector algebra we are doing. Very simple. But still some students may have some issues. That's why I am going slow and showing you all the steps. So now you see this multiplied by this. So this term multiplied by, so x bar w transpose times x bar w minus this term multiplied by this term minus this term multiplied by this term as usual plus this. Okay. Now for the simplification of this term, we'll give you that I am just segregating the parameter term w transpose w, and believe me, this is very, very permissible and doable. You can just check with the dimensions. So w transpose into w times x bar transpose times x bar minus twice this and this, and that is twice x bar w transpose into y plus y transpose y. With me? So this is my expression of the objective function in vector form. Now I can differentiate. W is now vector. Everything is a vector here now, right? The level is a vector, m cross 1 vector. This is a vector, n plus 1 cross 1 vector. This is a vector, n cross n plus 1. This is a matrix actually. Okay. So every term is a vector. Here every term is a vector. And I am differentiating this vector function with respect to a vector. Okay. And making it to 0. And don't worry, this differentiating with respect to vector is just like differentiating with a scalar. So here, you see here, you can think of w transpose w, w squared. So if you differentiate with respect to w, so 2 into w, x bar transpose, and then this is x bar. Okay. So it remains as it is. Minus y x bar transpose, and then you are differentiating with respect to w, so 1, it is 1, and then y remains here. And this is independent of w, so it is 0. And that for optimum value of the objective function, I know that that has to be 0. And beautifully now, so 2 cancels out. Okay, you see I have got W x bar transpose x bar equals to x bar transpose times y. So this has gone here. So this is there. And then straightway W is equals to x bar transpose um, into x bar. Okay, so just multiply it by x bar. So and then x bar transpose remains. So just both the direction, both the side, you multiply it by inversion of this, right? So if this is A, so you multiply both sides. A inverse equals to A inverse, as simple as this, transpose y. So that's how. And A inverse equals to unitary matrix. So W is getting separated. So this is very simple, right? And now you get W momentarily, like magic. Okay. So you have x bar transpose times x bar inverse x bar transpose times y. That's great. Let us call this matrix A. So if you have samples, level samples, momentarily you are getting parameter. Isn't it great? So no iteration, nothing else, right? So just we have applied the linear regression principle, that is objective function, differentiate the objective function with respect to parameter and evaluate parameter from that condition. Okay, so that's the linear regression methodology, and we have done it. Okay, so W, you have got this. Now look, what is the problem here? No problem if the features are not that large. But really, if the features are large in number, then inverting this matrix is a problem. Because as you know, the computational complexity of inversion of a matrix is big O n cube. So that's a problem, problem number one. So we'll elaborate. First, talking about a problem and all, we'll just see that what we have achieved. So ready-made, you have got the feature, level, and then the ready-made parameter you are getting using this formula, right? That is the beauty. So advantages, the solution is analytical in nature and comparatively very fast. And the choice of moderately, and this is the choice for moderately large number of features like n equals to 100, 1,000, several thousand, even 10,000, no problem, because today's computational facilities can easily compute this kind of dimensions matrix. Okay, no problem. The disadvantage or the disadvantages are when you see this matrix A, that means I have just in a short form I have written this matrix. When this matrix is not of full rank, that means you have a huge matrix and you have collected data, maybe either one row or column, they become redundant or repetitive in nature, or a linear multiplication of one row, say it is x and another row is 2x. Then that's a problem, because the matrix A will no more be of full rank, and then determinant will be 0, and then you cannot calculate the inversion. Okay, so that's the problem when the matrix is not of full rank, and this is a possibility when you collect data and data is used in number, so you never know where you have made some mistake. And computational cost, yes, it is n cube, but there are some methods, okay, for inverting in Gaussian method, Gauss elimination method, it is order of n cube. So you see, it's large, isn't it? So number of features, if it is 10,000, it's quite large. So this is n cube, order of n cube. And this Trasens also developed some algorithm. He could reduce the complexity, is order of n to the power log 7 to the base 2, which is approximately is coming to the big O n 2.80 something. But again, there are some problems of programming this. It's a little bit awkward. Uh, Apart from these two, computational cost and this singularity or the um, non-existence of the inversion. Apart from this, if these two problems are not there, always as a machine learning engineer, you should use this. And your features is not in the range of million or something like that. First, go for um, this normal equation and write them in the form of matrix form, and then you get, okay, W is there, so predictor is design, predictor is the moment W is figure out, predictor is defined, and use the predictor for prediction. So that's the story of dealing with a large number of features. Well, not so large, okay, 10,000. But next class, I will just tell you when the number of features are really, really large, say in the range of some million, okay, and it may happen. See, we are collecting data of our population, 1.4 billion people, and many features you can just tell them. Number of samples also is 1.4 billion, and we could figure out many um, income, age, height, weight, nutrition level, these, and you can think of many features um, which can make life really complex. So how to deal with machine learning problem when the problem has really large number of features is the discussion for the next class. Still then, stay happy and stay safe. Bye bye.